Hi, my name is James Chu, and welcome to Renaissance Timing University. Today, I'm going to talk about device skew. First, I'm going to talk about what it is. Second, I'll talk about the causes of device skew. Third, I'll talk about the different types of device skew. And lastly, I'll talk a bit about the measurement of device skew. So, what is device skew? Well, from a microelectronics definition, device skew is the time difference of a signal along the path. You can also think of device skew as the phase difference between two different signals. Now, why is device skew important? Well, device skew is important for digital designers because they talk about timing margins and they need to meet setup and hold times. Device skew is defined in JEDEC, and basically JEDEC is a council that meets to define these standards for the microelectronics industry. Now, what are the causes of device skew? Well, device skew could be caused by IC layout. So IC layout, you had different routing paths. These different paths have different parasitics, which could lead to skew. Second, the package. The package, for example, if you have a QFN or a BGA, these different packages have different parasitics, which lead to different propagation delays. Third, the output buffer. So take, for example, if you have CMOS, is rail to rail, it has a capacitive load, or if you have a differential signal like LVDS, which is a smaller swing, and it's a 100 ohm termination. So different loads, different swings could lead to device skew. Clock distribution. So take, for example, if you had two different signals going through two different devices, these two different devices have different delays. So at the final output, you're going to have a skew. So what are the different types of device skew? Well, the first one is output to output skew. So take, for example, this diagram right here. You have a common input and you have these outputs here. You can also talk about channel to channel skew, or you could just talk about channel skew. So if you take, for example, these three buffers here, which is the first channel, the top, and then the bottom channel, these three buffers here. So assume they all have the same load. Now, channel skew would be the worst case skew between any of these signals within this top channel. But whereas if you want output to output skew, it would be basically the two worst case outputs of any of these outputs across all the channels. So basically output to output skew is the worst case, whereas a channel skew is just the worst case output to output within a channel. Now the second one is input to output skew. That's the propagation delay. So take, for example, you have an input here, rising edge output. It's basically the delay between the input and the output. One thing that I wanted to mention is that the conditions are all the same here. So all of the loading here is all the same. Temperature is the same, voltage is the same. The last one is process skew. So in process skew, we're talking about multiple devices. Here, this is just one device. So if you have multiple devices, for example, you'd be looking at the worst case output of one device versus the worst case output of another device. And so basically, you're looking at the process variation of the manufacturing process. And it excludes things like temperature, input slew rate, frequency, loading. So all of that is excluded. The only thing is you're looking at a device to device. And just because the manufacturing process, each of these devices have a little difference. So lastly, the measurement. So if you're measuring two CMOS signals, it becomes relatively easy because you're looking at the mid rail for the first signal and then the second signal. But if you're looking at a differential signal, well, then you need to look at the zero crossing. And if you're comparing, for example, a CMOS input and a differential output, well, then you would need to look at the mid rail of the CMOS, and then you look at the zero crossing of the differential. The other thing I wanted to mention was different probes. So we have active probes, passive probes. Passive probes, they're low cost. Active probes are a bit more expensive. The active probes, they're meant for higher frequency. These active probes provide gain, and they have a lower capacitance. So for high-speed signals, active probes are a lot better. The other thing is active probes. They're good for differential signals because they have matching P and N paths to the oscilloscope. Thank you.